So now that we've talked about exponential expressions and exponential functions, we want to try to investigate the inverse functions of the exponential functions. Now, we don't have anything nice that's already in our wheelhouse from our earlier algebra, so we've got to say, okay, let's call it something. Logarithms. Logarithms are going to be the thing that are the inverse functions of exponential functions, which means that, this is the whole key thing about the exponential functions, is that variable power, logarithms need to give us access to the power. Logarithms need to be equal to powers. Logarithms need to be a fancy way of going, boom, there's the power, baby. So let's take some of the language that we've got and let's start doing this rearrangement. If we're going to have this logarithm, that's an awfully long word. Let's shorten that down. Let's call it log. Since we've got the word base as an important vocabulary word of our exponential functions, let's have that base also show up with our logarithm. And let's have it show up as a subscript. So the logarithm base b. Now, if logs are supposed to give us access to the powers, then let's have the power be the y. And that leaves us with one other piece of the exponential expression, the exponential version of this. That would be, well, if we did that power, what is the result? The result of doing that power, if we call that x is going to be the thing that's inside of the logarithm. So there's this correspondence here with these pieces. We have the base b, we have the base b. Logarithms are equal to powers. And the other thing, well, that's the thing that's inside the logarithm. That's going to be the thing that is equal to that exponential expression. So we have just those three key pieces that are appearing in both the exponential version of things and the logarithm version of things. So the log base b of x, just by itself, can be interpreted as what power on the base b will generate, will give us, will crunch out x. Log base 2 of 8. So what power on our base 2 is going to give us an 8? 2 times 2 is 4, and times 2 again is 8. Oh, there we go. 2 to the third power. So what power? Third power. The log base 2 of 8 would be equal to 3. It's what power? Third power? That's that answer. So as long as we're keeping this in mind, we can do this. Yeah, except we've got to make sure that we're still really comfortable with all of those rules for exponents. So let's do some examples where we're rearranging things and trying to answer those questions. What power? Starting with this example here. The log base 3 of 1 over 81. So let me say that again. The log base 3 of 1 over 81. It has already, with the way we're saying it, this kind of connection to our generic function notation. F of x. Log base 3 of 1 over 81. It's already got some connections with the way that we're saying things. That's going to lead us into that logarithmic function business very shortly. But what power on the base 3 will generate the number 1 over 81? We've got to backtrack things. We don't know what that power is. We're going to start with the 1 over 81. We're going to backtrack that eventually to a 3 that has a power attached to it. Well, we can start out based on our rules with the fact that a 1 over 81 can be turned into an 81 with a power. We would have to remember that the power that we need is a power of -1. Then we can say, hey, you know, based on my times tables, I remember that 81 is also 9 squared. And then my rules for exponents say that we can multiply those powers together. So a power of 2 times a power of -1 is a power of -2. And then, hey, the 9, I know that from my times tables, that's a 3 squared. And so, once again, multiplying our powers together, 3 would have a power of -4. That's what we needed. 3 to what power? Well, 3 to the power of -4. So let's throw a little color emphasis on that -4. What power did we need? We needed a power of -4. That's what we've got. That's what that is. This logarithm business is equal to -4. That's it. That's what we needed. What was the power on the 3 that we needed to have that would crunch, crunch, crunch and spit out a 1 over 81? And we can check that out and make sure. We can say, all right, well, let's try it. 3 raised to the power of -4. Does that give me a 1 over 81? And depending on how you want to check that out with your calculator, you got a few ways that you can do that. But yeah, that's what we got. Hey, wait a minute. This doesn't say log. What? We've got a couple of special logarithms. This is one of them. The other one is actually going to be featured in the next example. This logarithm is abbreviated with the ln, and that is in reference to what we call the natural logarithm. We're going to talk a little bit more about that when we get to talking about logarithmic functions. But the main thing with the natural logarithm is that we have this special base e. Like what we saw with our exponential functions, that base e being special still, we want to be able to reverse that. The natural log is going to be reversing any base e stuff. So, hey, look at all that e stuff showing up in there. What power on just a single base e is going to give us this e cubed over 5th root of e squared? Woo! All right, well, first of all, we've got that root that's down there. So we've got to remember that our roots tie in with fraction powers. We're going to keep the power of 2, and the root itself is going to give us the denominator of that fraction. So that's going to give us an e to the power of 2 over 5 down in the denominator. Then we've got our rules for exponents that say, hey, when we have division like this, we're going to take the power from the top minus the power from the bottom. And when we simplify that, e would have a power of 13 over 5. Well, that's what we were looking for, e to what power? So that power seems to be at 13 over 5. That means we have our answer here, 13 over 5. That's what we're going for. So e to the power of 13 over 5 would get us the same thing as this calculation here. And then one more. Okay, at least we're back to log. What? We've got log, but there's no base that's listed. Well, the common number system that we use is the decimal number system, and the decimal number system has base 10. So when we say log and we do not put a base on there, that is automatically base 10. We call that the common log because it is based on that common number system that we all use, the decimal system. So log, automatically making me say to myself, what power on 10 will give me square root of 1,000. Okay. Well, we just said roots tie in with fraction powers. So that's a square root, also known as the second root, also known as the denominator of my fraction power, would have to match with that second root. Well, what about the numerator? Well, the 1,000 doesn't have a power already appearing, but we can view that as having an invisible power of 1, so 1,000 to the 1/2 power. 1,000, though, is rather nice that we can drop that back to a 10 with a power of 3, and as we had mentioned earlier, we multiply those powers together, and we would get a power of 3 over 2. So the log of the square root of 1,000 is 3 over 2. So this is our basic idea. Logs are equal to powers, really trying to hammer away at that idea with these examples, as well as also, kind of jog our memories a little bit with those rules for exponents that we might need, especially when we take this idea and revisit it later on when we have equations to solve.